So, hello everyone. In today's video, we'll continue with our chapter solid state. So, in the previous discussion, we discussed about the packing in three-dimensional closed packing from two-dimensional square closed pack structures. We discussed that how from a square closed packing, there are only two dimensions. When we switch to the third dimension where all the three axes like x y z axis molecules are present forming a 3D arrangement of molecules. There we saw if these kind of arrangement is there, like molecules exactly at a distance, exactly behind one molecule the other molecule is present, then this kind of square closed packing layers will be formed. So the type of pattern here is a type pattern, and the lattice is simply cubic lattice. Moving to the further, we understood like what are the type of voids. Tetrahedral voids are those voids which are formed at the center of the four spheres. As you can see, four molecules are present, three are in one plane, and one is present in at the gap or the void generated between the three spheres of the lower plane. So it is present in the in between that space, and hence it is generating a small void over here. So this is called a tetrahedral hole. While if the molecules present in the second layer are present in this fashion such that they are not covering the depression of the first layer, exactly as in the case of the tetrahedral void. If they are not exactly covering the depression of the molecules in the first layer and are arranged in this fashion, then the void generated in between those six molecules present in two layers, then the kind of void generated over here is an octahedral void. It is formed at the center where the six spheres are joined in the form of an octahedron. So, coming to the three-dimensional closed packing from two-dimensional hexagonal closed packed layers. If the second layer is present over the first layer, okay, that means if the two-dimensional layer is considered as A, like molecules are present in x direction and y direction, and it is they are forming layer like this. And the second layer, which is above the first layer, is in such a way that the spheres of the second layer considered as B are placed in the depression of the first layer. That means they are generating an octahedron void. Three molecules, see these black three molecules and A. If B is present at the depression of that, that means with B, considering these three molecules, a tetrahedral void will be generated. Okay, and are placed in the depression of the first layer. This give rise to two types of void: tetrahedral void that I showed you over here, and if we consider another set of molecules like a these three, and over that if we consider these three molecules B and B, the void which is the present written where C is written, this kind of void generated is called an octahedral void because it is generated because of the uh, co- three molecules present in the first layer and three molecules present in the second layer, which are not exactly present at the depression of the first layer. That means the C1 is the octahedral bond. Now coming to the if this third layer, if this the third layer over the third layer, if third layer here I mean like if I till now I just told you like how if the second layer is present exactly in the depression, or if the second layer is present not over the depression, then these kind of void is generated. If the third layer uh, is present in covering the tetrahedral voids, I told you na if Hmm, where can I show you? Okay. So, here the tetrahedral voids of the second layer may be covered by the sphere of the third layer. That means it gives rise to an AB-AB pattern. If you see that here, if we see, so the molecules generated over here, uh, see B and B are present, A is present over there. That means the void generated behind A, and considering these three molecules forming a tetrahedral void, and the pattern will be generated as A, B and A. That means A layer is present, then B layer is present, not in the depression of the first, present in the depression of the first layer. I mean, and above the A molecule, again above A molecule is present. That means the pattern is AB type pattern, and the three-dimensional structure is called a hexagonal close packing structure. The coordination number here will be 12, and some example of this is manganese and zinc. These metals form these kind of patterns. And if the third layer is covering octahedral void, that means I told you na, if three molecules are arranged and A, you can see these three molecules, one this A, second this A, and third this A. The three molecules present in the first layer, and the second layer, the molecules are present not in the depression of the first layer exactly, and the third, and there will be a void generated over here, which is and the third layer, that is C, it is not present exactly at the molecules, exactly over the molecule A. It is present rather the void at the void generated by the two layers. So this kind of pattern generated over here is gives a pattern of ABC type pattern, and the three-dimensional structure is called a cubic closed packed structure or face centered cubic structure. The coordination number here also is 12, and these kind of pattern are formed by copper and silver. Coming to the packing efficiency. Packing efficiency is a percentage of total space occupied by the constituent particles or atoms in a molecule. We know there is a unit cell where the particles are present at the corners or at the face center or at the body center or at the any two faces of the unit cell. So how, but there are some space which is vacant. So packing efficiency tells basically how much space is occupied by the particles in a unit cell. So this is the formula for the packing efficiency. Packing efficiency is volume occupied by the spheres divided by total volume occupied volume of the unit cell into 100, since we are calculating the in percentage. So, for a primitive unit cell where the particles are present only at the corners of the unit cell, so volume occupied by the atoms. So how many atoms are present in this unit cell? In the previous video, I showed that in a primitive unit cell, the coordination number is 1. That means these 8 molecules present in the corner has a total contribution. Each molecule at this corner has a total contribution of 1 by 8. So 8 molecules into 1 by 8 gives a contribution of 1. I told you now that each one of this has a contribution of 1 by 8. So 8 such molecules having a contribution of 1 by 8 gives gives a Z value, that is value with the mm, uh, mm, overall value of the particle present in the primitive unit cell is 1. So the volume occupied by the one atom, overall one atom, is 1 into 4 by 3 pi r cube. This is the volume of the sphere, since we are considering molecule to be in a sphere fashion. So the volume occupied by the atoms is 4 by 3 pi r cube. And the packing, as per the packing efficiency formula, volume occupied by the atom. So here I wrote like 4 by 3 pi r cube divide by volume of the unit cell. We know that volume of a unit cell, this unit cell we are considering as a cubic form. So volume of the unit cell will be a cube. Okay. But this cube is actually like this fashion. Those particles are actually touching each other. So this length A Can you like relate over here? So it is like this. These particles are basically touching each other. So applying basic algebra that we know. So this is the length A from here to here. And we know this is the radius R for a sphere. So A will be equal to 2R. Okay. So volume of a cube is basically A cube. So volume of unit cell will come out to be uh, 2R cube. 2R whole cube. That means 2 cube is 8 and R cube is like this. So when we put in this R formula, when we put it over here, then it will be 4 by 3 pi R cube divided by 8 R cube into 104 percentage. That comes out to be 52.4 percentage. That means if molecules are present in the primitive unit cell, then the packing efficiency of the atoms or the molecules present in this fashion will be 52.4%. Okay. So, coming to the BCC structure. In a BCC structure, we know that molecules are present at the corners and molecules are present at the body center. So, contribution of this molecule at the corner is 1 by 8. Okay. And we have 8 such molecules. So, contribution present due to the molecules at the corner will be 1. And there is one molecule present at the body center. So the contribution will be 1 for this molecule since it is not shared by any other unit cell. 1 into 1 will be 1. So for overall for the BCC, the number of particles in the BCC will be Z equal to 2. 1 plus 1 gives 2. So the as per the packing efficiency formula, we know that volume occupied by the 2 sphere is in the unit cell. Okay. So 2, this means this 2. Okay. Total number of actually contribution of the spheres is 2 and the volume of those sphere is 4 by 3 pi r cube. Okay. Now how this thing comes? So in the BCC structure, we have basically the molecule present at the body center, because of which in the case of primitive unit cell, you saw na particles are basically touching each other. The particles present in the corner, those particles are basically touching each other. Okay, in though that SCC primitive unit cell we saw, simple cubic unit cell, the particles were touching each other. But in case of BCC, if we see, particle has a molecule present in the body center. So the molecules won't touch each other, rather there will be a gap between that. But the body center present in the unit cell will actually touch the spheres present diagonally to each other. So these spheres will touch each other. That means that this sphere will touch this sphere and will be touched by diagonally present this sphere. That means if we consider only one side of this, that is the this distance is basically equal to the diagonal. So for the diagonal of the cube, we know that it is equal to under root 2a. Applying the Pythagoras theorem, no? Right? The hypotenuse square is equal to base square plus length, height. For a Pythagoras theorem, we know that for a triangle, the height square is equal to base square, height square plus base square is equal to hypotenuse square. So the diagonal comes out to be under root 2a. So for this under root 2a, this much length, how many spheres are there? 1. So 1 radius, these 2 radius, okay, these 2 radius and this 1 radius. Let me change the pen. So this is the radius for this one sphere present at the corner. This will consider as 2 radius since it is a diagonal. So this is the 2 radius present at the center of because of sphere present at the center, and this one is the radius for the third sphere present at the corner. So 2a is equal to 4r. So as we know that volume of the cube, that volume of the unit cell that we are considered is under a cube. So writing it in another way, we'll can write it as no a is equal to 4 by under root 2. Excuse my writing, please. It is difficult to write over here using mouse. So a cube will be cubing this equation, that this is 4. Okay. Cubing this equation will be, sorry, uh, this will be 4 cube. I'm really sorry. This is not actually the uh, this is actually present at the body center, so that will be come out to be under root 3. I told you for the FCC where the molecule is present at the face, but here the molecule is present at the body center, so it is not basically touching this one but rather touching the uh, rather it is touching the sphere present over here. So this whole length will be under root 3a for body center. The diagonal distance between the two opposite corners of the sphere is under root 3a, and that's how it will come out to be a is equal to under root 3a is equal to 4r. So a will be 4r over under root 3. So cubing this equation will we can write it like this. I told you for this is actually for FCC. What I told you over here, I did a mistake over here. It is actually under root 3a for BCC. So solving this equation, it will become out to be 68%. Okay. Now coming for the FCC. As I told you in the previous over here, no. So considering this distance, molecules are present at the phase center. 6 phase center. So this distance will be under root 2a. Diagonal distance for a square is under root 2a. Under root 2a will be equal to 4r. Okay. I told you above, no? Under root 2a will be equal to 4r. So the packing efficiency here you can see clearly. This is the radius of one sphere. This is the diagonal of the one sphere, and this is the radius of another sphere. So this distance, that is under root 2r, is equal to 2a is equal to 4r. So 4 atoms are present at the FCC, as I told you earlier as well. So 8 atoms are present at the corner. So 8 into contribution of each is equal to 1 by 8. And atoms present at the face, there are 6 atoms present at the face, and each has a contribution of 1 by 2. So this comes out to be 1. This comes out to be 3. So 1 plus 3 gives 4. And this 4 is the 4 atoms over here. Okay, 4 atoms into volume per atom is equal to 4 by 3 pi r cube. Volume of the unit cell, as I told you, under root 2 is equal to 4r. So A is equal to 4 by under root 2r. They did the cube of that, and the volume came out to be, the packing efficiency comes out to be 74%. Coming to the radius ratio. Radius ratio is actually refers to the radius of the, sorry, it is radius over here. Typing error. It is radius. Is a It is actually ratio. The radius ratio refers to the ratio of smaller ionic radius by the ratio of larger ionic radius. That means radius ratio will define by radius of cation. Cation is smaller by radius of anion. Okay. See over here, it is also written rho is equal to radius of smaller cation by radius of larger cation, larger anion. Anion is larger, no? So, how can we define that the packing is stable or unstable? If the cation is too small, that means it will be moved freely. That will give an unstable structure. But if some cation is perfectly in size, then the packing will be really nice. If packing is nice, that means the rigidity or the other properties that are making a solid nice or proper arranged solid, crystalline solid, that will be good. But if the size of the cation is too large, that will not cause a proper arrangement, because of that these gaps will be generated in between the molecules present in the solid. That's why this is the stability limit. Okay, if a proper sized cation is present in the voids, that means the arrangement will be good. So this is the arrangement of the this is basically the radius ratio is the ratio of cation over anion. So for a tetrahedral void, if we consider for a tetrahedral void, if a cation is between, if the radius ratio for the cation and anion comes out to be in this range, that means that will be more stable, that solid will be more stable. So these are the basically the limits for the various uh, cations present in the voids of the molecule, voids of a solid crystal. So if voids are linear, that means the radius of the cation should be so small that the ratio comes out to be 0.155. If triangular planar molecules are present, like molecules are present in this fashion, so if a cation has to come in this void, in the triangular planar void, there the cation should be so small so that the radius ratio comes in between 0.155 and 0.225. If it is a tetrahedral void generated by four molecules, then the ratio of then the cation size should be that much, where the ratio comes out between 0.225 to 0.414. If it is an octahedral void, then the ratio must be in between 0.414 to 0.732. If it is a cubic void, then it should be in between 0.732 to 1. If it is a closed packing structure, then the ratio should be 1. So, coming to the relation between edge length of the unit cell and radius ratio of cation. I told you in the previous packing efficiency slide. So, for SCC, molecules are directly touching each other. That means the edge length of the unit cell is basically equal to radius of the two spheres that are actually touching each other. So, the value of the edge length is basically related equal to 2r. For FCC, molecules are present at the face of the unit cell. So the diagonal here over here is basically a combination of four radiuses. That is the radius of this one, two radius of this center one, and the one radius of this corner one. So applying the Pythagoras theorem, hypotenuse square is equal to height square is equal to base square. So that's how it comes out to be, relation comes out to be 4r is equal to under root 2a. For BCC, the molecule is present at the body center. So here we will consider the diagonal with the spheres touching the molecule present at the body center. That will be the diagonal of the cube. And for the diagonal of the cube, we know that it is applying the same Pythagoras theorem again. So BD square, which is the hypotenuse, BD over here is the hypotenuse. Let me see. So BD over here is the hypotenuse. Hypotenuse square is equal to height square is equal to base length square. So FD square is equal to A square. So BD comes out to be, what is this FD? FD is equal to 2A, because it is the basically the um, it is basically under root 2a. No, in the FCC we saw that it is basically under root 2a. So under root 2a square is equal to 2a square, and that's how it comes out to be under root 3a. Hypotenuse comes out to be under root 3a. That's how the radius is related as under root 3a by 4. Coming to the other topic, which is density of the unit cell. Density, what is density? Density we define as the mass of the unit cell by volume of the unit cell. So, how will you calculate the mass of the unit cell? For mass, you need to know that how many molecules are present. So, for example, for primitive unit cell, you saw that Z is equal to 1. For FCC, you saw Z is equal to 4. For BCC, you saw Z is equal to 2. So, to find out the density of the unit cell, first you need to know the mass of the unit cell. Mass of the unit cell varies for the different type of unit cell, as I told, because Z varies. Mass depending upon the Z into mass of the each molecule, okay, divided by Na. Why are we taking Na? Because it is the Avogadro number, okay. And then the volume of the unit cell is equal to A cube. We know we are considering cubic unit cells, so the whole formula will come out to be Z into M over Na into A cube. If we divide by Na, because we are taking molar mass over here. Molar mass is equal to mass of 1 mole of molecules, but we are considering atoms. So atoms present in the unit cell. We are not talking about the moles. That's why we are dividing the Na, Avogadro number. So density of the unit cell is equal to effective number of atoms, which is defined by Z, into mass of the unit cell M divided by the volume of the unit cell, where mass of the unit cell or mass of effective number of atoms or ions, M is equal to atomic mass or formula mass. N is the Avogadro number, which is 6.022 or 6.0323 into 10 to the power 23. A is the edge length of the unit cell. An element crystallizes in the structure having FCC unit cell of edge length this. Calculate the density. This is a question for you. So please calculate the density for this. Coming to the another topic, which is crystal defects. Crystal defects are basically defects, we are talking about the solid. So solid, we discuss different type of solid that includes crystalline solid and amorphous solid. But it is not always so 100% sure that the crystal is 100% pure or 100% crystalline. It will contain some irregularities in the arrangement of the atoms. So here we will discuss how those defects are present. What are those defects? So crystal defects are the basically irregularities in the arrangement of the constituent particles. So type of defects we'll discuss over here: point defects. And so first is the point defect. Point defects are the irregularities or the deviation from the ideal arrangement around a point. Basically, these are the irregularities with around a point or an atom in the crystalline substance. So it could be stoichiometrically or intrinsic or thermodynamic defects. So basically, a particular atom or a point, at a particular atom or a point, there will be some defect. It includes varieties under this, which is stoichiometric defect. Stoichiometric defect in further is of 4 types: vacancy defect, interstitial defect, Schottky defect, or Frankel or dislocation defect. We'll discuss in detail about this. The other category is non-stoichiometric defect. It includes metal excess defect and metal deficiency defect. The third one is impurity defect. And the second type of defect is line defects, where the line defects are the irregularities or deviation from ideal arrangement in the entire row. In the point defects, we were discussing that irregularities are around a point or an atom, but in the line defects, irregularities are present in the entire row of the lattice points. So, starting with the point defect, we discussed now there are 3 types of defects: stoichiometric, non-stoichiometric, and impurity. In the previous slide, I told you that point defects where the irregularities are arranged around are of the ideal arrangement. Irregularities are present around a point. So these are of three types: stoichiometric, non-stoichiometric, and impurity defects. So point defects are stoichiometric, non-stoichiometric, and impurity. What is stoichiometric defect? Stoichiometric defects are the defects that do not disturb the stoichiometry of the solid. Okay, the number of cations will be number of the equal to the number of anions here. So these are present in non-ionic solids. Okay, when so in non-ionic solid, these are of two types: vacancy defect and interstitial defect. And in ionic solids, these are further of called Schottky defect and Frankel dislocation defect. Okay, we'll further discuss all this. So have patience and try to understand systematically. Okay, points defects are those where the irregularities are present around a particular point or at the position of the particular atom. Okay, these I told you that these are of three types: stoichiometric, non-stoichiometric, and impurity. Stoichiometric are those where the overall stoichiometry of the molecule of the solid is not disturbed. Okay, these are of further four types we'll discuss. Non-stoichiometry are those where the stoichiometry of the solid is disturbed. This includes metal excess defect. Metal excess defect is the defect due to excess of metal cations. I told you in the stoichiometry, number of cations and number of anions will be equal, but in case of this non-stoichiometric defect, the stoichiometry is disturbed. So how stoichiometry will be disturbed? Either the number of cations will be more, or either the number of anions will be more. So in the case of metal excess, that means cations. Metal are cations generally. So metals will are more. Metals are present in excess. Reasons are anionic vacancy. How the number of metals will be more? If anions are lost, there are anionic vacancy or presence of some extra cations. These are the only two ways, no, where the number of cations will be increased in the solid. So as you can see here, the anion present, see the minus charge is basically showing the number of anions, and the positive charge is showing the number of cations. So because of the space over here, the electron is present, not the anion. Okay, overall basically the number of cations are more than the number of anions. This is called a metal excess defect. Metal deficiency defect are those defects where the absence of metal ions from the lattice site. These are electrically neutrality is maintained by the adjacent anion having higher positive charge. Here in non-stoichiometric defect, even though the number of cations and anions are not equal, overall charge will be or the solid will be neutral. Here, even if the anion is missing, electron is present, that is making the whole crystal neutral. In metal deficiency defect, basically the metal is missing. In the metal excess, anions are missing or metal are present extra, but in metal deficiency, metals are missing. And but this positive charge of the metal is maintained by adjacent ion having higher positive charge. Third, coming to the third category, which is impurity defect. These are the defect in the ionic solids due to the presence of the impurities present in them. Okay, this is simple, basically because of the impurities. So you can see the sodium chloride crystal here is shown. Sodium ion present, chloride ion present. Overall, please notice, overall it is electrically neutral. Number of positive charge is balanced by number of negative charge because strontium is present. See, strontium contains Sr2 positive. Even though one sodium ion is missing, but overall this two positive charge balance the positive charge by negative charge. So overall positive charge and negative charge are equal, even though strontium is present in the, as the impurity. So, talking about the detail about the stoichiometric defect, I told you these are the four types over here. So, we'll discuss that in detail. Stoichiometric or intrinsic or thermodynamic defects. For non-ionic solids, these are basically where the stoichiometry of the molecules are not disturbed. This includes vacancy defect and interstitial defect. Vacancy defects, you can see a crystal is said to have vacancy defect when some of the lattice sites are vacant. These defects result in the decrease in the density of the substance. You can see the green molecules present showing the presence of molecules in the crystal. Uh, at two positions, these molecules are missing. That means vacancy is generated at those positions and it is generating a vacancy defect. Okay. Interstitial defects are where a crystal is said to have interstitial defect when some constituent particles or atoms or molecules occupy interstitial site. See, these are the position where atoms should be present, like in here you can see. But these molecules present in the interstitial sites. That means they are present in excess and they are actually increasing the density. Okay, density of the molecule. Here density was reduced because particles were missing. Particles are present in the extra number, that increases the density. Coming to the defects in the ionic solid, which include Schottky defect and Frankel defect. Schottky defect, the defect where equal number of cations and anions are missing. It is basically the vacancy defect in ionic solids. I told you that overall the electron, the neutrality of the solid remains. So here in Schottky defect, both cations and anions are missing from their position. You can see positive cations, positive anions, positives are cations and negative are anions. Here in this square, positive charge is missing, and here in this square, yellow colored square, the negative charge is missing. So overall, both the cations and anions are missing from the solid. It is the vacancy defect in the ionic solid. It decreases the density of the solid. Schottky effect is shown by the ionic substance in which the cations and anions are of similar size. Okay, it includes examples like sodium chloride, potassium chloride, cesium chloride, and silver bromide. Okay, coming to the Frankel defect. In this defect, smaller anions, usually the cations, are dislocated from the normal site. So here you can see cations, this the square shown over here in the pink, it is missing from its usual position and is present at some other position in the interstitial site, the green positive charge. Please see my laser point. Over here it is present. That is showing that it is basically a dislocation defect where the from the usual normal site it is present in some interstitial site. It does not change either the density because the particles are not basically missing. Where the Schottky defect, particles were missing, both the cations and anions were missing. That was causing a decrease in the density. But here overall the density remains same. Frankel defect is shown by the ionic substance in which there is a large difference in the size of the anions. It includes zinc sulfide, silver chloride, silver bromide, silver iodide, etc. Coming to the classification of solids on the basis of their, now we'll discuss about the electrical conductivities of the solids. So we know that solids would base on the base of their electrical conducting properties. Solid can be characterized into three categories: conductors, insulators, and semiconductors. Conductors are the solids, those solids which with having a conductivities ranging between 10 raised to power 4 to 10 raised to power 7 ohm inverse meter inverse are called conductors. Insulators are those whose conductivities are range between 10 raised to power minus 20 to 10 raised to power minus 10 ohm inverse or meter inverse. Semiconductors are those whose conductivities lie in between 10 raised to power minus 6 to 10 raised to power 4 ohm inverse and meter inverse. So to understand how solids conduct electricity, we need to understand band theory. A metal is characterized by a band structure. In this theory, we consider a metal and we study it via considering band structures. The highest filled band is called valence band and the lowest unoccupied band is called conduction band. The gap between the two bands is called forbidden band. Band theories, different types of solid are based on their electrical conductivities. Here you can see the highest filled band is called valence band. And the lowest unoccupied band is called conduction band. The blue one is basically the valence band where the molecules are present. How molecules will conduct electricity? Okay, at some point molecules will be present. Molecules, basically we say molecules containing electrons. So at this level molecules with electrons are present, and they are present highest field band. This is the highest field band, and it is the lowest unoccupied band, and the gap between them is low for conductors. They are basically overlapping, and the gap is generally called a forbidden energy band. So okay, forbidden band. So for conductors, the valence band or conduction band overlap. That's why they conduct electricity, because the movement of electrons from the valence band to the conduction band will be easy. That's why they are conducting. But in case of insulators, this forbidden zone, this band gap between the valence band and the conduction band is so large that the electrons can't move from here to this higher energy band. That's why they can't conduct the movement of electrons, and they are called insulators. While in case of semiconductors, the forbidden gap between this valence band and the conduction band, it is smaller than the insulators. That's why some electrons, I am not saying all, as in the case of conductor you saw now, these bands were basically overlapping, so the movement is very easy. But here the gap is smaller energy gap, so some molecules and some electrons may jump from the conduction band and show some conductivity. Electrical conductivity of conductors increase with the rise in temperature. So let me tell you, with temperature, if temperature increase, that means the particle energy is increasing. If the energy of the particles containing electrons will increase, those electrons will easily jump from valence band to the conduction band, and hence with increase in temperature conductivity will increase. So types of semiconductors: intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors are those in which the forbidden gap is small. I told you in the previous slide, no? So conduction band is there, and in the band theory we study the conductivity of the solids. So as per that we consider two bands, valence band and conduction band. So intrinsic semiconductors are those where the forbidden gap is small. Only some electrons may jump to the conduction band, and they have very low conductivity. Example, silicon and germanium. While extrinsic semiconductors, where impurity is added to the intrinsic semiconductor. So, which due to the addition of the impurity, it is basically a conduction band with a small gap. The conduction band and the valence band has small gap here. Okay, the gap is small, but here the impurity is added. This is added because of which the conductivity will increase. So how this impurity is added? The process of adding appropriate amount of suitable impurity, due to which increase in conductivity of due to which we observe the increase in conductivity of the semiconductor. This process is called doping. So type of extrinsic semiconductors, the N type, where impurities is added, that increases the number of electrons in the semiconductor. The P type semiconductor we'll discuss. So in the N type semiconductors, the impurity which is added in the intrinsic semiconductors is an electron rich impurity. Like for if you are adding silicon, silicon is containing 4 electron in its valence band. Like outer band, it contains 4 electrons. So if you add an element to the silicon from the 15 group, that will contain 5 electrons. Okay, so before 5 electrons, 1 electron is, this 1 electron is extra. Say silicon has 4 valence electron, phosphorus has 5 valence electron. Adding phosphorus to the pure silicon results in the surplus electron. 1 extra electron is there, and this 1 extra electron is the free electron, which will increase the conductivity. Electrons are basically causing the current. No, the movement of the electron is current. So the free electron, it will move freely and therefore increase the conductivity of the solid. while in the case of p-type semiconductor, these are formed when silicon is doped with the electron deficient group. So you might be thinking like, if electrons are causing the movement of electrons are basically defining the movement of electrons is basically defining the conductivity, then how come we, if we are providing one less electron, how less electrons will cause a increase in the conductivity? It is actually because of the hole generated. As you can see, silicon has 4 electrons, 4 valence electrons. Okay, boron added from the 13th group, it has 3 valence electrons. Okay, this hole is there. Adding boron to the pure silicon results in the lack of an electron and it becomes a hole. So because of this hole, these electrons will keep moving in this hole. So if electron will move in this hole, hole will be generated over here. Then this electron will move in this hole, then hole will be generated over here. This electron will move in this hole and a hole will be generated over here. So due to the continuous movement of electron in the hole and continuous regeneration of the hole, there will be a continuous movement of electron, and that's how, even if you are adding an impurity from the 13th group, overall conductivity will be more than the intrinsic semiconductor. So now we'll discuss the property, another property of solid, that is magnetism. Magnetism is basically how, see, how will you define magnetism? Every substance has some magnetic properties. The origin of this property lies in the electrons. Okay, each electron in an atom behave like a tiny magnet. Atom, every atom basically every atom contains electrons, and each electron behaves like a tiny magnet. Its magnetic moment originate basically from the two types of motion. See, you know the electron. See, electron will move around. This is a nucleus. So electron rotates around the nucleus in the orbits, and also electron rotate around its own axis. It will keep rotating around its own axis, and it will keep rotating around the nucleus. This is a nucleus, positive charge. Okay, because of the two motions, self rotation around its own axis and because of the motion around the nucleus in the orbit, it is generating showing magnetic property. So classification of the substances based on the magnetic properties. Paramagnetic substances are those substances which are weakly attracted by the magnetic field. Weakly attracted by the magnetic field, these are due to the presence of one or more unpaired electrons. Basically, the magnetism is coming because of the free electrons. So, if electrons are unpaired electrons are present, that means that substance is paramagnetic. Diamagnetic substances are weakly repelled by magnetic because in the diamagnetic substances, free electrons are not present, all the electrons are paired. So if you see, like the let us consider this sign as the magnetic moment of electron. If two are up, two are down, and one is up, let us consider 5 electrons are present. So if this is the fashion, that means 3 up, 2 down. So overall the magnetism is 1 by 2. Considering up has a spin of up has a magnetism of plus 1 by 2 and negative has a spin of minus 1 by 2. So these two positive are cancelled by these two negatives, minus 1 by 2, and this overall the one up electron is present, which is giving a spin of half. But in case of diamagnetic, let us consider 6 electrons. So 3 up and 3 down. 3 s is equal to plus half are balanced by s is equal to minus half. That means there are no that means all the electrons are paired, and because of all the electrons are paired, there is no magnetic moment in the substance, which is called diamagnetic. Paramagnetic substances are those which are strongly attracted by the magnetic field. Here, the number of unpaired electrons are more, and which cause them strongly attracted by the magnetic field. Antiferromagnetic substances have equal number of parallel and antiparallel magnetic dipoles. I showed you, these arrows. These are arrows can be are basically the magnetic dipoles because of the free electron. So either they will be S is equal to half or S is equal to minus half. So they have even the antiferromagnetic substances has S is equal to plus half and S is equal to minus half exactly equal. That means they have net zero dipole moment, and they won't show any magnetism. Paramagnetic substances have unequal number of parallel and antiparallel magnetic dipoles. Therefore, they result in some dipole moment and hence will show magnetism. These are basically the classification of the substances on their magnetic properties. We'll discuss some other chapter in the next video. Thanks. We'll discuss polymers next time. So thank you everyone for your time. Bye bye.